come to Minden in central Germany to visit my friend of many years, Dieter Beikirch. Over many decades, Dieter has built up one of the finest private collections of valve-era German avionics in the world. Not only is the collection comprehensive, covering important aircraft communications and navigation technology from the First World War until after the end of the Second, incredibly, almost everything in his collection is in original working order. With over 80 set-piece exhibits in the collection, we've got a near impossible mission to give you an overview of this extraordinary collection. Still, if we manage it, we will, in effect, have given you an overview of the best of German avionics in the vital era of the vacuum tube. To do this, we promise to pack in as much as possible in the shortest time. Later, we'll cover the collection and the individual desks in more detail, but today's mission is to give you a taster of the most historically significant parts. We've got a lot to show you, so let's dive straight in.
The first radio was installed in the German aircrafts. It is the Telefunken D4 transmitter receiver, and this is thinking from 1917. Yeah? Now we have not enough wind. Here you see the Morse key. For example, I give one time, whatever you know, SOS.
Any minute now there's going to be a helicopter overhead trying to rescue us.
The current is going in the antenna, here by lamp.
It's not the visible spark itself, but the conductors leading to the spark that creates the radio or electromagnetic waves. From a chart on the wall, Dieter explains that the spark transmitter generates these rapidly decaying or damped electromagnetic waves, and you can see how the power rings down after each spark. If the key is dabbed quickly, we get a dot. If it's held momentarily, we get a dash, and so telegraphy, using Morse code, can be sent. But a spark system like this does not allow telephony or voice transmission. With just a few steps, Dieter moves to 1930 and a giant leap in radio communication technology with the Telefunken 378 long-wave transceiver. This system was developed for commercial aircraft and was used by all aircraft in Deutsche Lufthansa's European fleet, but it was quietly adopted for use in the first military training aircraft of the new German Air Force. It would become known to the world in 1933 as the Luftwaffe, in open breach of the Versailles Treaty. The radio was designated FuG 21, and like the spark gap technology before it, this radio system was also limited to Morse telegraphy, transmitting on a fixed range of frequencies between about 300 to 500 kHz. But crucially, it used the new thermionic valve or vacuum tube technology. Dieter explains that from 1933 this new technology allowed radio transmissions to carry the human voice.
With the microphone, yeah. And in the 1934, here was the first radio station for the fighters, because the fighters want not make telegraphy, they want talk, yeah. And this is the first radio station, FuG VII, for the telephony. So.
The Telefunken FuG III onboard radio system saw service from 1933 and was developed from an older Marine or Navy radio to respond to the needs of Germany's new Air Force, the Luftwaffe. Intended for aircraft with 2 or more engines, the main difference between the naval receiver and transmitter was the dramatic weight reduction and changes to the power supply. The wind generator, essential to the earliest versions of the FuG III, when used with the Heinkel 111 or Junkers Ju 52, was typically located on the top of the aircraft. The fully working version of the FuG III we see here is presented as a ground station. It was also used like this in mobile units as well. Dieter points out that the FuG III was essentially an older system called into service as a stopgap in the early years of the Luftwaffe. But in the mid-1930s, electronics technology was evolving rapidly, and Telefunken had developed new vacuum tubes that were much smaller and had more reliable base fittings. These new tubes weren't only more efficient, their robust mounting and connection systems made them more suitable for military use as well. Eager to exploit this new valve technology and bring their radio communications up to date as quickly as possible, the Luftwaffe offered a competitive contract to Telefunken and Lorenz, two of Germany's most competent manufacturers. The specifications called for a modern, modular, high-performance radio system for aircraft with 2 or more motors. The result was one of the war's most sophisticated aircraft radio systems, the Lorenz FuG X. From 1939, it became the standard equipment for larger aircraft with several crew members. This is a complete FuG X laid out once again as a test station. It was used like this for workshop maintenance and training. Dieter explains that the Lorenz design exploited the new smaller transmission tubes and the new compact P2000 pentodes, allowing an impressive reduction in the size and weight compared with earlier radio sets.
This was very big. This is one radio in the same dimensions like before. Yeah, very, very small and not so heavy. And the specialty was you can take this, put this here in the frame, ready.
The Lorenz quick release system was mandated on all aircraft radio installations. From the FuG X we moved to a smaller system, the FuG XVII. The FuG X operated on long-wave and short-wave and allowed communication with ground stations on long-wave and plane-to-plane or tactical communication on short-wave. The FuG XVII was a new system that employed ultra-short-wave or VHF with a much shorter range and was an ideal tactical radio for close air support for aircraft with a 3-man crew, pilot, observer and gunner. Morse could be transmitted and all crew had headphones and microphones so they could talk to other aircraft and ground stations. The FuG XVII was another instrument from the Lorenz stable and of course used their rapid replacement system.
Easy, put out, put in. Yeah. Okay, this was FuG XVII.
Just 2 steps across the room take us to the FuG XVI. It sounds like we should have looked at this first, but in fact it came after the FuG XVII. The FuG XVI became the standard radio telephone set with ultra-shortwave VHF used in all German aircraft from large multi-engine aircraft to single-engine planes until the end of the war. In larger aircraft with 2 or more motors, it was used together with the FuG X, but in fighter aircraft it was used on its own. The set was used exclusively for telephony or Vox communication with no telegraphy or Morse code option. It was intended for use by just one operator, not 2 or 3 as we saw previously. Dieter explains that once again the set is presented in the form of a workshop test panel, where every component can be tested, including the power output of the instrument. The system was also used in setups like this in ground stations and mobile stations in vans and trucks.
Yeah, okay, this was Prüftafel 16, the last radio in all fighters and all German planes.
In the same room we have the FuG XVI ZY or ZY. This is the same VHF transceiver used in single-seater aircraft for Vox communications, but here we have additional equipment for Y-Verfahren or Y control, in which aircraft were fitted out as fighter formation leaders that could be tracked and directed from the ground. The display shows the principal equipment as mounted in the Messerschmitt 262 and 109. The thin panel on the right-hand side carries the remote controls located in the cockpit. The system worked by using ground transmitters known as Y stations. Each Y station could control 5 fighters. The Y station would send out a signal picked up by the FuG XVI ZY. This signal was repeated by the transponder and sent back on a frequency 1.9 MHz lower than the transmitted frequency. Using a radio direction finder, the angle was measured and the range was calculated by a timing system connected to the transmitter and the receiver.
And what you see here, this was a FuG XVI-Z. So, okay, I think this was the communication. And now we go to the direction finding.
Dieter explains that the ground station operator would listen to the transmitted signal from the aircraft and take a bearing from the signal using the direction finding antenna. The operator zoned in on the signal until the transmission was strongest. The bearing was then plotted on a map as a chord from the ground station to the aircraft. Combined with a second direction bearing from another suitably remote ground station, where the chords crossed is the aircraft's location. This information was then relayed to the plane.
But now we come to the own piling. When the aircraft has its own pile system, here we see the direction finder was called in German Peil G4. Yeah? And it was so, on the top from the aircraft was this antenna. And here is a pointer, and the pointer has to stay always in the middle for the correct flying on the beam. Yeah? But you have to steering with the aircraft to find this right way.
The Peil G4 is one of the first onboard direction finding systems, and it can indicate direction directly from the received signal. Previously, navigating an aircraft could be a complex and labour-intensive process for the crew.
I start this station. This is a direction finding on the aircraft, but the direction finding was only on the roof of the aircraft, and you have to move the aircraft and watch this instrument. Yeah, so this you can listen, and now I go to the direction finding. Yeah, and you see here, that is a signal from the airport. Yeah, and you see here is very strong. We are nearly on the airport. Yeah, and when it's in the middle, we are on the right beam. Now we are to left. Now we are to right. And so you find the shortest way for finding the way. Okay? What we have seen before was the plane can find the way only in the fly direction.
The G4 direct approach navigation system that we looked at in the previous segment required the plane to fly directly to the radio beacon. With the Peil G5, the aircraft can take bearings from a radio beacon in any direction, 360 degrees around the aircraft, and reconcile it to the compass, allowing the aircraft to navigate using any number of beacons, limited only by the strength of the radio signal. The key to this is the rotatable bearing antenna, or Peilrahmen in German. In the older version of the G5, the loop antenna is controlled from within the aircraft by a cranked knob and a flexible drive cable that connects to a worm gear system in the base of the antenna. The angle of the beam relative to the plane's direction of flight can be read from the antenna controller.
The correct way is shown on this instrument, like we have seen this before. Yeah. This is the system Peil G5. Yeah. What you see here is the last direction finder. Was also used until the war, but was also used by the French aircrafts until the 1960s. Yeah, what we can see here first is a new compass. Yeah, here the antenna is not outside on the roof. This is inside, in the aircraft roof. Here you see the antenna turning by hand, right or left, to find the correct beam from the radio station you will see. In this room, we see also a way to find the correct place for the aircraft. So, in this system has two antennas. First antenna is this. For the beam detection. A second antenna is under the fuselage from the aircraft to detect the signals in front of the airfield, and here we have the receiver for the beam, and this is a receiver for the signals in front of the airfield. Here's the motor generator. Here's the indicator. We are left or right from the beam, and here's the selection for the channel, special channel you need for the airport. I adjust this. First, I have to start. So. Yeah. So. Okay. We can start with the. We can start to show the system, how it works. Okay. I show here now the beam was used to fly from French to England. Yeah. Also the pilot had to listen dashes, dots. In the middle was the permanent tone. So,
from here, the pilot must carefully regulate the plane's altitude and speed. Now the bombardier listens out for the continuous tone of the second transverse beam, called oda, at a position 10 kilometers from the target. On hearing the tone, he presses the start button on the X clock. When he hears the tone of the third transverse beam, the elba, he presses the start button again. The X clock now calculates the time to the target from the known 5 kilometer distance between the oda and the elba beams and the speed over the ground, and triggers the bomb release automatically. When the red hand overlaps the black hand, the bombs begin to drop. The details for the bomb release were set on the X-clock ground equipment, but the final exact moment of release was calculated by the X-clock on board the aircraft.
So, we have seen the first beam, X Wotan I, and here we come to the next version, more simple. We have only one main beam, but only one cross beam. Before we had 3 cross beams. Yeah, so this was more easier, but it was also not so exactly. The circuit from the bombing was nearly more 500 kilometers. Yeah, so that was the name Knickebein, because the name came from this knicking antenna. The receiver was the same receiver like we use for the blind landing system, what we have seen also before. Yeah, and here on this instrument you can also see you are correct on the beam, you're left or right. It's the same manner was the beam made, left points, right dashes. Yeah. Okay, this was all for the Knickebein system. Also, we have seen the Wotan I X system, we have seen the Knickebein system, but this system was disturbed by the English. And so the German made another version, not with the left points, right dashes. They made another system, very complex.
The chart on the wall here is headed Y Verfahren Kampf Wotan II, or Y procedure in battle Wotan II. With the Y method, only a single beam was used. There were no transverse beams. The Y ground station determined the aircraft's distance to the target, and the bomb release time was also determined from the ground using an X clock like we saw earlier. The onboard devices were modified versions of the FuG 17 communication system working on 42 to 48 MHz. Two-way communication was unaffected. To measure the distance, a pulsing tone was transmitted to the aircraft, which the onboard FuG 17 transponder received and instantly bounced back to the ground station at a lower frequency. The distance to the aircraft was determined by the round-trip propagation time of the radio signal, with the Y ground station measuring the phase offset between the outgoing and incoming signals to determine this. It wasn't required that the pilot fly the beam, as with previous beam navigation methods. The Y station ground controllers relayed course correction information directly to the pilot.
So, yeah, okay, here the pilot can see the course again, yeah, and this is the receiver, yeah, and also transmitter to talk with the other people, and also to send back the signal for the measurement, yeah. And this is a very complex system that the English not so quickly find out how it's going with the beam. Yeah. When we talk about the beams, was this the last system was the measurement, the distance measurement by electric. How it works.
The Y device used a single narrow beam from a ground station laid over the target and transmitted as a series of pulses. A transponder on board the aircraft received the beam signal and immediately retransmitted the signal back to the original station. By analysing the phase difference between the outgoing and incoming signals, the distance to the plane could be calculated with impressive accuracy. The aircraft was not required to fly the beam, as with earlier systems. Ground controllers would plot the position of the aircraft and give direct instructions over the radio to the pilot to correct his position.
Here we have a transmitter. This transmitter sends a signal to the aircraft, but also on this wave. And from the aircraft comes back the signal, yeah, by a transponder, and what's received in this receiver. And from this receiver, also the signal goes on this tube. So, but there was a difference from to the plane back to the ground station, and this difference is shown here on two beams. They are not together, so they out. Now you can see the two lines, and have to put the two lines together in kilometers and fine with this. Now I can look in a table where it's D and 0, 5. And from this table I can look how is the distance to the aircraft. This is a typical method to measurement the distance. Okay, shortly we see here electronic beam steuerung Siemens K4, very important, and was plenty made for plenty aircrafts in all in the world. What you see here, this is the motor, the pump motor for the hydraulic. You see here a demonstration from the rudder. Yeah, you see here the magnetic compass. You can see here the point of the correct direction. You see here the compass rose, and here you see the Steuerhorn, yeah, to drive right or left, or you can also make this so right and left, and so on. Here's the main switch, and here's the emergency knob. When the electronic is broken, you can pull it, and you can normally steer the aircraft.
The Siemens K4U or K4U we were just looking at only helped the pilot with compass course navigation by providing automatic rudder control. But for the aircraft's position in terms of attitude, pitch, climb and turning rate, level and so on, the pilot had to constantly monitor a range of instruments like the artificial horizon, turn and airspeed indicators, and correct his position from moment to moment. To relieve the aircrew of this workload, especially on longer flights, a method of controlling elevators and ailerons was developed, and a basic 3-axis autopilot was the result. Dieter explains that due to the sensitivity of the enclosed equipment, the ultra-clean environment of the hermetically sealed casing was purged with nitrogen gas to minimize the risk of corrosion and other changes occurring to the equipment. The automatic system, developed in 1941, received its control data from the Patine Horizontmutter, the core of which was a highly stable gyroscope from which all aspects of flight attitude were picked up electrically. The results were displayed for the pilot on a simple-to-read display system that instantly showed the aircraft's attitude relative to an artificial horizon.
What happened? Yeah, maybe the aircraft goes down. This is a horizon. Yeah, goes down or goes high or makes a bow. Yeah. And this was automatically steered. Yeah. You see here the test panel for the altitude meter for very low distance. Yeah. The range was from 150 to 750 meters over the ground. Yeah? And with this system, you can fly very nearly to the ground. Yeah? This was very important when you fly over the sea, and aircraft with the normally altitude meter with air pressure follows you. Yeah. So.
You mean when a fighter aircraft that only has a air pressure altimeter?
Correct.
It's very imprecise.
Yeah,
very difficult to fly at this altitude.
In the darkness.
Yeah.
In the darkness.
Very dangerous.
And the antennas were so under the wing. Right wing, left wing. You see here's the transmitter, here's the receiver. Yeah. What you see here is the test panel for the FuG 102A.
The FuG 102A was a radar altimeter with an altitude range of up to 4 kilometers, or just over 13,000 feet. It was used to establish the correct bombing altitude. It functioned like a typical radar system. The transmitting antenna was located under the right wing, and the receiving antenna under the left. The transmitted signal is directed down and reflected by the terrain beneath the aircraft. The rotating marker on the display screen will have advanced proportionally by the time taken for the reflected signal to return to the aircraft. The higher the altitude, the longer the return time, and so the further the display mark will have progressed around the display. The system gave an immediate and easy to read presentation of the current altitude, day or night, regardless of visibility.
And the receiver, here's the transmitter, and here's the power supply. Very difficult. Yeah. very plenty tubes in this and so on. A very difficult part. What we see here is the last detector from the German aircrafts to find the English H2S system. H2S was very new and has very high frequency and very short wavelengths. And for this new frequencies, the Germans has nothing. So, but they won't find now the bombers with the H2S system. And what they have done, they took a special antenna. Yeah, this antenna was turning on top from the fighters. Yeah, and this antenna turning was also seen on this screen. So when there was in this direction was an English bomber, they got on the screen a point, yeah, a bright point, shown here in this explanation. Here's the English bomber, yeah, the normal English bomber, and with the H2S radar on board. Here's the German fighter with turning the antenna, and when the antenna is going, looking to here, then they got on this screen a bright point. So they have to turn the aircraft in this position to fly to the English bomber, yeah, and to fight him, yeah. And this you can see here on this screen. And to test the system was this box that the soldiers told them FuG, yeah, yeah. So it works, and you can simulate the H2S radio from the British aircraft, yeah, and can see it works or not.
One question.
Yeah.
Did this system give them any range information? It gives them direction information, but did it give any range information?
Ranging not, only the direction.
So they still had to use their eyes.
Direction only. Yeah, but they can change how bright, very bright, nearly, slowly bright, far away. Yeah. What you see here is a test panel for the tail warning radar. I started. Okay, so off, on. So the tail warning for the German aircraft, to be sure that no fighters behind them. How it works. What we have seen on this screen, the radar principle is so, what impulse, radar impulse, go out, and then the system is waiting for a reflection. And if there are some behind us, behind the aircraft, then you get here a point. Yeah, also a point. And when the point is here, it is very dangerous for the German aircraft. Yeah? And in what distance this reflection is, you can here see, this is always 3 kilometers. Yeah? When the point is here, no problem. But when the point is here, very, very nearly, yeah, then you have to go down. Yeah? Transmitter. Receiver, yeah, junction box, power supply, and this is the side. Yeah, this was a tail warning. Okay. Okay, we go here. So, what we see here is the latest German radar system for the night fighters. Yeah? To find in the night the English and American bombers. Yeah? This was done with this all equipment. I have made this equipment so like it was on the test panel in the workshops and the air bases. The parts of this system, most important, the indicator for high, low, and left and right. Yeah, this is the indicator. Then we have the antennas switch. This switch makes the antenna on top together, left, right together, or down together, yeah, automatically. But you can also do this by this antenna switch, by hand, when you press these knobs, yeah, and then you can see only here or only here, yeah. So this is the transmitter, sends the signal to the aircraft, then signal comes back from the aircraft, and was the receiver, and with this wheel you can adjust the receiver so that you have the best indication. Yeah. So here is the power supply, and here is the generator for the high tension, and this is the knob off, on, and the fuse. Yeah. On these two tubes, yeah, you can see a line, and here is also a line. On this line, you can see the targets, the enemies in the distance. Every point was 2 kilometers. Yeah, you can see in your direction how much it is more high or more low. Yeah, and on this display you see the same in your direction, what is more right or more left.
The FuG II20 SN2 had a maximum target detection capability of about 8 kilometers or 5 miles. In a moment, Dieter will switch the system on and you'll be able to see what these screens really look like, and amazingly, what the system might have sounded like to the crew aboard a German night fighter. But first, let's finish our roundup of the FuG II20 SN2 hardware by looking at the antennas.
Okay, here you see a picture from a German night fighter, Heinkel 290. And on this front of this aircraft were 4 antennas, yeah, for the FuG 220 SN2. Yeah? And what I have made, I made these antennas here in reproduction, and you see the antennas in the correct dimensions, in distance, and also in this length, according with the working station. Yeah.
So Dieter is going to power it up now and use a test signal generator so that you can see what the cathode ray tube displays looked like, and, incredibly, what it might have sounded like to the crew of a German night fighter. This sound came as a bit of a surprise to us, as it's coming through the radio microphone receiver we have attached to our camera. Now, we're not saying that the crew would have heard it as loud as you're going to hear it. The builders would have done everything they can to make sure that the electrical interference from the low-frequency radar system did not interfere with the onboard radio transmission and the intercom system. But trying and achieving are different things. And when you operate radio detectors and amplifiers close to other powerful radio transmission systems, even ones working on very different frequencies, it's pretty common to have harmonics and radio frequency spillage from the transmitter leaking into these other circuits. So I'm pretty sure the sound you're hearing would have been familiar to the night fighter crews that used the FuG II20. They may have only heard it in the background, and then only if they pressed their headphones hard to their ears, but I'm sure this interference would have found its way into some piece of equipment on the plane, and they would have heard this sound.
Left. High left. Where are the targets? Okay? I close. Okay, what you see here is a test panel for the radar system FuG 200, called also Hohentwiel. For what was it used? It was used to find the ships in the sea, yeah, special the convoys were coming from America from Canada to support the English. Yeah? So, and how it works. Here you see the transmitting antenna. Here you see the left antenna, and here you see a right antenna. So, how is it working? The antenna, the transmission antenna, sent a signal, and back came from the ship's reflection to left or to right. Is the signal from right more strong than here? Yeah, you have to turn the aircraft so that the reflection from left and from right have the same length. And then you are flying direct to the ship and can fight it. And the distance you can see here on the valve tube with scale names. But it is difficult to show how it works because we have no ship here. Yeah. So, and for this gave an artificial target, künstliches Ziel. Yeah?
Artificial target.
And this I have done here, and you can see what the operator sees. Yeah? Here's a ship target in 3 kilometers. Yeah? Or for example, here in 6 kilometers. Yeah? This is what the operator sees on this Sichtgerät. On this
cathode ray.
Yeah, okay, yeah. So, but very important, and I have to show this because I'm so surprised about this wonderful system. The company was Lorenz, yeah, and the Lorenz has made this, yeah. These are the transmitter, a push-pull transmitter, yeah. Also, here are the tubes, and this is transmitter in push-pull, and the power of this was 30,000 watts, 30,000 watts peak. Yeah, and here is the modulator. The modulator, how many times came this signal in a second? Yeah, and this was made with this very nice tube. We have here then more 800 amperes. 800 amperes was running through this tube. Yeah, okay. Receiver is also a very good made. Here you see also very nice tubes in this time. Yeah, here too. Yeah, okay. This was the FuG 200, called in Germany Hohentwiel.
The BZA was an analog computer system designed to process a range of critical aircraft sensor and pilot inputs to calculate the precise bomb release point, typically for aircraft like the Ju-88 and the Arado AR-234 executing dive bomb attacks. The BZA computer was able to process moment-to-moment critical aircraft data, including altitude, speed, wind, track, and dive angle, as well as target data related to position and geo-altitude. The information was updated in real time and presented in a simple active terrain overlay reticule of the Stuvi dive bomb site.
That is the aircraft comes and goes so down and let fall in the bomb. But to have the right position, he has to look in this glass. He sees the target, and also in the glass you see a mark. And when the mark is over the target, then he has to press and leave the bomb. Yeah? So, but when the aircraft flies, it has speed. We have wind from right and left. We have different air pressure and so on. And all these parameters was calculated by this computer. This is a electromechanic computer. Yeah, you see here when you see this are working here. And all this movement from the aircraft changes the dot was here going. Also the speed or the height. Now we are 2 kilometers up. Yeah. Oh, here's the speed. Yeah. So these parameters depend on the correct point of target. Yeah. So, and what I can show you, he has to look here inside, and there is a point, and this point has to stay over the target, and then you can press. Yeah. This is a function of this very difficult system. Yeah. I can show something. Here you see the motors give the position to this point. Yeah. Straight. Yeah. And here speed. Yeah. And how it's done. This is the electric system. Yeah. The same moving makes this. This was also in FuG X the same. Yeah. I move here, and for the computer, sits here, moves here. Now I start this test system. Yeah. And I have to put into the calculator some parameters. Yeah. For example, now ready, really ready. I have to put in the calculator some parameters. Wind. I have to that is the altitude from barometer, altitude meter. I have to put inside the speed. So And I have to show you the angel. Here you can see. Here you can see the altitude. Yeah.
The Henschel Hs293 was a radio-controlled glide bomb primarily intended for use against ships. The Hs293 was the world's first guided missile to be effective in combat. Today we would call this type of weapon a standoff missile, and with around 30 hits on Allied shipping with several sinking, the Hs293 was the world's most successful anti-ship missile until the French Exocet developed 3 decades later. Based around a 500 kilogram airdrop bomb, the weapon was manually guided into the target by sight using the target cover method. This dictates that the missile must remain in the line of sight of the controlling bombardier so that he can keep the missile superimposed on the target. Here the Hs293 is dropped from a carrier aircraft, a Heinkel HE-111. After a second or two of free fall, the missile gets clear of the aircraft and begins to drop behind. A small liquid fuel rocket engine ignites and burns for 10 seconds, propelling the glide bomb to about 900 kilometers per hour, around 370 to 400 kilometers per hour faster than the Heinkel. The missile must be ahead of the control plane and between the bombardier and the target. A test target, the size of a small ship, has been set up in the Friesendorfer marshes just northwest of Peenemünde. The missile was powered by a small Walter rocket engine, delivering a thrust of around 600 kilograms or 1,300 pounds, and was mounted in a pod underneath the main body. Presented here are the principal components of the FuG 230 radio receiver and guidance control system on board the missile. This is the receiver unit. We can see the P2000 pentode valves here. And 2 Siemens telegraph relays to switch the directional control surface servos. And on the other side, another row of P2000 valves. The unit with the 2 plugs facing the camera is essentially a filter system that discriminates the important control signals from the total signal received. This is the distribution system that everything else connects to. A small motor generator or umformer here. The stabilization gyro is seen here. This gyro keeps the wings level and is vital to the control stability of the missile. Dieter demonstrates the gimbal release mechanism automatically activated at launch. The missile has no rudder on the ventral stabilizer, so left and right steering is accomplished by ailerons on the trailing edge of the main wings. The gyro stabilizes the missile and restricts any tendency to roll by positively restricting the bank angle and restoring level flight after an aileron movement command is executed.
And here's the special motor for 500 Hertz and so on. Here we see the bombing man who is steering the bomb by eyes with this joystick. Yeah, and what he has to do there? For this, I have to open the machine. Yeah, this machine is turning. Yeah, and you can see what he makes when he makes so. This is a rudder for high, up in the sky and down in the water. Yeah, so the steering is working. Yeah, down, high, and here left and right. Yeah, so was the steering. And how was done this?
The Hs293 uses a pulse mode control system. The noisy mechanical nature of the joystick surprises
There are
some,
two wheels.
but the simple motor-driven system allows the control switchgear in the box to generate a unique pulse time pattern that's transmitted to the bomb and translated into control surface positions. The fundamental frequency, about 25 Hz, is fixed. Only the pulse lengths vary depending on the joystick positions.
I hope you can see this. Yeah? Okay.
We've seen the steering by radio, but Dieter points out that concern about British and American electronic countermeasures led to the development of a wire-guided system. Up to 4 reels of thin wire could be used for a maximum range of 30 kilometers, or just short of 20 miles. The long wire had a high electrical resistance, so the system had a special 200-volt power supply.
This was we told to this Drahtlenkung, steering by wire, but later was also a steering by television. So it was in the bomb in front, camera, television camera, and you can watch this on this screen. Yeah, that was the last, but this with the television was not okay and was never in action.
Just before we end, we're going to show you an extraordinary and rare piece of film. Captured in 1944 using a cine camera set up to record the CRT display, like the one in the picture, in the carrier aircraft used to launch and control an experimental Hs293 D. The view we see is from on board the missile as it glides at about 350 kilometers per hour towards a test target of what are probably disused barges anchored off the coast between Usedom and Lubmin. Boom. And that brings us to the end of this video. We've done pretty much what we set out to do, which was take a tour of Dieter's stunning collection and highlight along the way some of the most historically significant German aircraft electronics. If you've stuck with us this long, it's a fair bet that you're as keen on Valvera avionics as we are, and especially as it applies to the Second World War. Later on in this series, as well as exploring the history and function of fermionic valves, we'll be homing in, as usual, on some instrumentation, like the control electronics of the V2 missile. So if you don't want to miss anything, don't forget to subscribe. It does help us on the channel as well. And maybe click the bell icon so that every time we upload something new to the channel, you get a notification. Until next time, from Dieter and me, bye for now.